I've already described in a separate screencast how to use a Excel spreadsheet with Solver to carry out nonlinear regression for enzyme kinetics. And in this screencast, what I want to do is describe a different method from in the other screencast on determining confidence limits. The spreadsheet that shows how to carry out this, and that I'll show you in a few seconds, is located on the LearnChemE site at this link. And now let's look at that spreadsheet. So just to review quickly, we're fitting kinetic data where we vary substrate concentrations S and measure rate R using two parameters, Km and Vmax. Here are the values we obtain using Solver, and here's the sum of the squares that we minimized with Solver. So we had experimental measurements of rates in this column, and then in column E we have the values calculated for these parameters. And then the difference between the experimental and the calculated squared we summed up in this yellow cell. And it's the same value that's up here in this cell. And this is what we minimized to get a good fit using nonlinear regression. Well, I've already done that and obtained these two parameters. Now I'm showing confidence limits that we calculate, 95% confidence limits. And calculate those by a method different than I explained in one of the other screencasts. So let's look at how we do that. So what we're doing now, and you'll notice I created a column here. Here's the value that minimizes the least squares, and here's the sum of the squares. That's the same value that's here up in this cell. Now, what we've done is pick values around the best fit, smaller values and larger values, keeping Vmax the same, and then use Solver to calculate what the sum of the squares. Well, the sum of squares is not going to be, it's not going to be as good a fit. So you can see these numbers are bigger. We go in each direction, but that's what we want to do to determine the confidence interval. So what I do is fix Km at let's say at 450. And then I'm going to go to Solver. I'm going to vary the Vmax value again to minimize the sum of the squares. We've named this cell. So when I do solve, it'll come with a solution. Now we have a different value for Vmax. And now we have 00125. That's this value right here for 450. And what we've done is repeat that same procedure for probably more than values I needed to, but just to demonstrate the idea, for number of values on either side of our minimum sum of squares. And then we've plotted those values. So we look here, what we have is a plot of the sum of the squares. I varied Km around that 545 minimum. And here are the data points. And then what I've drawn is this orange line. So the orange line is calculated in this formula, the sum of squares. And this is the sum of squares at the minimum value. P is number of parameters, which in our case is 2. df is number of degrees of freedom, which is number of measurements minus number of parameters, in our case is 8. And this is a formula in Excel that calculates, as explains here, this is a formula that calculates the inverse of the right-tailed S probability distribution. I'm not going to explain the reason for doing this, but if we use this formula where 0.05 is because 95% confidence limits, then 5% in fractions is the value that we put here. So I've determined the value that's in this yellow cell that's using the formula I just explained, and you can see it's written up here. And then that corresponds to that orange line in the figure that we looked at earlier. And then the confidence intervals are where this orange line intersects the blue line. So this point here, and then I did the same thing for varying Vmax, right? So this is the case where I picked the value for Vmax and then minimizes sum of squares by varying Km. Made another plot, the same orange line, same locations, same formula. Again, the intersections corresponds to the confidence limits, and so those intersections are then the values that are shown here. You notice it's not symmetrical. If it was dramatically asymmetrical, then this method wouldn't be very accurate. And if it's a very shallow curve, instead of steeply increasing away from the minimum, it wouldn't be very accurate. But it's a different method that just is appropriate for calculating confidence limits, in this case 95% confidence limits.